Okay, well, we can, on that note, we can start the talk. So, Bill McDonough, please lecture.
Okay. At some level, this is a little bit, it's like the rest of the talks you've heard. It's intended to be interrupted throughout. And the other proviso is at some level, it's a slightly schizophrenic talk because I had one talk, and then some people had mentioned some ideas and topics, so I thought I'd cover them. So I'll do a little bit of both in that regard. I'd like to start off with two things. Independent of looking at other people's notes, I put together these ideas as what I would call fundamental. And I thought it was also instructive, so in preparation over the weekend, I actually looked at a number of the past CITER lectures. And in fact, the next slide is the opening first, second, or third slide from the very first lecture by Don DiPaolo and Stan Hart. It was the geochemistry lecture. So it's interesting to put in perspective because I think we're hitting the same topics, but using very different words. So if I were to go through, what is the energy budget of the Earth? What the heck is a geochemist talking about the energy budget of the Earth? I mean, we'd heard some of the geodynamicists talking about that. Well, in large part, really, a lot of my research has been underpinned by trying to establish the composition of the Earth, trying to establish the composition of the Earth's mantle, the silicate sphere, the crust plus the mantle, and the metallic sphere, the core. And in doing so, you come up with some numbers. You come up with numbers for all the elements in the periodic table. And in doing so, you definitively come up with numbers for what is the thorium, uranium, and potassium budget of the Earth. And also where it is distributed. And that, in essence, really becomes an important parameter for the geodynamicist. So, in fact, I actually find some comfort in knowing that my information set goes beyond a bunch of stinking geochemists. That is, I can actually deliver information that is of some use and testability in the geophysical community. So that is a driving force of my research. I'm not just doing it for the sake of geochemistry, but I'm actually trying to inform and discuss with how our information set provides information to the geophysics community. Okay, so the energy budget really is a story statement about what is driving plate tectonics, mantle convection, and the geodynamo. These are important parameters on the Earth system, and thus it's a useful piece of information to at least contribute to. How much of the Earth's energy? It's interesting. I've had a lot of problems this morning. I got up around 5. I revised things, but none of my revisions are saved. None of my revisions are saved. That means from about 5 to 7 this morning. None of the. Yes, this was yesterday's, and I slept on it, and I said, no, I want to change this. Okay, we'll go with it anyways. How much of the Earth's surface heat flux is due to primordial energy, and how much is due to the present-day heat flux? Well, in essence, that question is really asking if we have a certain surface heat flux, how much is actually due to potassium, thorium, uranium inside the Earth decaying and evolving heat from that decay moment, and how much is associated with the assembly of the planet, the kinetic energy associated with incoming particles, if they be planetesimals or even a giant impactor, that imparted thermal energy, it imparted kinetic energy into the system and is dissipated as thermal energy through time. So we do not know that ratio between radioactive energy and primordial energy. Since a large portion of this is really talking about the Earth's continental crust and dynamics associated with the Earth's continental crust, you have to also understand that you need to divide into two where this energy is stored, in the continents or in the mantle. At one level, this is a question of how efficient is the Earth system at differentiating or chromatographically separating potassium, thorium, uranium, highly incompatible elements, into the top 1% veneer of the Earth. Okay. That actually is informative at many levels, not the least of which is you have different scenarios. If you remember from the last 2 weeks, crustal growth curves. Imagine quickly, if you will, one crustal growth curve that essentially instantaneously grows continental crust 4.5 billion years ago. So whatever energy you put in the continents, you took it out of the mantle convection system instantly. So that actually has a significant penalty for radioactive power of the mantle. Alternatively, if you delayed continental growth until much later, at least half an Earth lifetime later, and put that energy into the crust, then you have a very different story for the energy budget of the mantle. So in terms of looking at the Earth system and the distribution of potassium, thorium, uranium from a geochemical perspective, it has significant consequences for a thermal perspective and therefore convective perspective. What proportion of the, because I felt that all these questions were actually saying the same thing. What proportion of the heat-producing elements are left in the mantle to derive? I will present to you at least a couple of scenarios. What I'm going to drive at the end of this talk is to say there is a significant amount of what we don't know, particularly when it comes to the composition of the Earth. And I know I've been very comfortable with a number, but in fact in the last few years, my comfort level is shooken. Not stirred, but just slightly unsettled. I really feel that we need to at least step back and say, I felt very confident about my numbers, but when I'm now starting to see some of the isotopic information, I'm not leaving that comfort zone, but I am shaking it up. I am really unsettled by the debates that are going on, and there's some pretty significant debates going on right now. So I'll try and get that unsettled feeling into your blood veins so that you do not assert the Earth is this. I don't think it is. Okay. And in particular, what are the building blocks to use to construct the Earth is the most important parameter that I'm struggling with right now. And it's of ancillary information to those of you who are interested in the dynamics of the continents. But it really is important information that will feed into your story. All right, so walking down memory lane. If I remember right, 2004, the first lecture was a geochemistry lecture, and it started, I guarantee this was the first, second, or third slide. I can't remember. Let's take a look at their questions. Let's take a look at their issues and see how it relates to my first slide that I made, be it the version that you saw or the version I actually worked on. How deeply does the near-surface material circulate into the mantle and on what time scale? Fundamental. In fact, to me, at some level, really, the return flow is just as important, and we're all talking about recycling. I'll actually hint on recycling. I often see the Earth's oceanic crust, covering 60% of the surface of the Earth, as essentially a snapshot of the mantle today. Its residence time at the surface is 50 to 80 million years. It's gone back in the mantle. And then whatever happens to it in terms of recirculation and reuse of that fuel, if you will, because it actually sucks up the thorium uranium, concentrates it by a factor of 10, and then brings it back down. So in fact, I'm looking at the system as what's happening is thorium, uranium, potassium. As a geochemist, we'll also measure what's happening to it in terms of the lead isotopes, the decay products of thorium and uranium. Also argon isotopes, the decay product of potassium. What is that recycling, and how has it affected the Earth's engine? On what time scale? Again, it asks the same question. Did we create the crust instantly at 4.5 billion years ago, or did we delay its creation by a couple of billion years? Does the mantle have large-scale chemical structures layering? At some level, geochemists do not know exactly what's down there. They'll assert brightly, but I tell you, I grew up in an age back in the 80s when many people were talking quite dogmatically about layering in the mantle. An upper mantle of mid-ocean ridge basalt composition, a lower mantle that supplies ocean island magmatism like Hawaii. We now have a very different picture, and perhaps driven largely by the seismological information that showed subducting slabs penetrating through the entire transition zone and going into the deep mantle. As geochemists, we basically can measure samples with high precision, high fidelity, but we really can't tell exactly where they come from. It's a logic train that depends upon the convection and geodynamicists that tell us that mantle plumes originate at some boundary layer, be it the core mantle boundary. So as geochemical information, it's interpretive. I can tell you definitively the composition of lavas at Hawaii look nothing like that at a mid-ocean ridge. And all I can do is use geophysical information to assert one's from a deeper region. And it's logical, too. Okay, so layering the mantle, at some level there is layering, but when I talk about major elements, I will show you where I think there's no layering, but I will tell you that colleagues of mine that have talked to at meetings just this year say there's a gross compositional boundary at the major element scale between the upper and lower mantle. Okay, so that's an important point. We do not know. Does the core mantle exchange material, the core exchange material with the mantle? I didn't talk about that topic at all this time, but it is an interesting discussion. There are some of us in the geochemical community who believe we have isotopic information that is carried straight from the core to the surface of the Earth in places like Hawaii using platinum group elements in their isotopic compositions. And in fact, that information set feeds back into another aspect of geophysics, which is when did the inner core grow? And in fact, the isotope geochemist might argue that the inner core didn't grow, grew almost instantly from day one. Some of the geodynamicists, Claude Power has actually been involved in some of this research, says that it actually makes more sense to grow the inner core late in Earth's history, perhaps over the last billion and a half years. And the tension that exists in that system is in part driven by whether or not we want radioactive elements into the Earth's core. That's a debate that's gone on for a long time, because if you have radioactive elements in the Earth's core, you have a different equation or a set of energy conditions for the core and whether or not it crystallizes. So I do believe that there's a lot of information exchange between the geophysics and geochemistry community. So that's actually important, is whether or not we have exchange material. I tend to not think so, but my colleague who I trust and actually have a lot of confidence in, Rich Walker, has been arguing for this possibility for the last decade, so keep it in mind. What are the characteristics of mantle convection in terms of its ability to stir and homogenize heterogeneous material? In large part, that's actually trying to ask the question by a geochemist, can we actually determine the length scales of systems of heterogeneity? Some people have studied the mid-ocean ridge from the North Atlantic to the South Atlantic, parameterized the material, the compositions of the materials, and said the length scales are X. So it would be very useful to understand the ability to stir, and the ability to stir actually is a measure of homogeneity or heterogeneity in the system. What features of mantle seismic heterogeneity are thermal and which are chemical? That actually at the very end of this talk I will actually try to highlight where we don't know. We listen to the mineral physics and seismological community. We think we might actually have ways to examine that question from a geochemistry point of view. And what aspects of mantle structure are congenital, of recent origin, or steady state feature? Not addressed by my talk, but I actually think it's a very important attribute of really the question of where we bring information into the domain. One thing that is actually congenital is we grew the crust, but we don't know when. Okay, so an important information set. So that's actually from the first CITO lecture, and it's a useful reference frame. I spent a fair amount of time on those two slides, and it was intentional because I think that's actually really far more important than maybe some of the other attributes of what I'm going to talk about. It's really much more trying to stimulate you to think about some things and perhaps make you a little uncomfortable with what might be your dominant paradigm. All right, so why do we want to talk about the mantle, particularly if we're going to focus on the top of the Earth? In fact, particularly if some of the talks that we're talking about dynamic topography, well, part of the topography is definitely part of the topographic statement of the surface of the Earth is actually controlled by what's going on in the mantle. And what is going on in the mantle is actually decipherable at some level from geochemistry. So we're talking about 2,900 kilometer thick layer, surfaced by about 35 kilometer continental crust or an 8 kilometer oceanic crust. Slightly different than the numbers that you saw before, and it's actually driven by the confidence level that I have in the paper that was written by Yu Huang that came out earlier this year. And we talked about that paper in the tutorial. I think the 35 kilometers is a little bit more correct because, in fact, there's a fair amount of continental crust that's offshore in the submerged region. Surface potential temperature around 1,500 Kelvin, but that number has a tilde in front of it because we don't know that number all that well. A lot of times we've been talking with confidence, but there are uncertainties in the system that really must be respected. I would guess that the uncertainty here could be somewhere between 50 and 100 Kelvin.
Well, that temperature seems very high today. Usually you're 1350.
That's in Kelvin.
Kelvin, sorry.
It's actually low compared to your reference, right? Yeah. In fact, yeah, it's a rounding off kind of number. I could have had 1600 if you like, and that would have really made you unsettled. And again, when we were talking about the Rayleigh number, I really loved CG's presentation because, in fact, in large part, it was really reminding us that there is a temperature difference at the top and bottom of the mantle that's definitely going to drive convection at some level. In addition, there's internally heating systems, but we don't know the level of internal heating because we just don't know how much radioactive elements is in there. Why talk about this? Because this actually is the phenomena called, the large portion of the Earth's mantle is likely to be made up of the source region for mid-ocean ridge basalts. Why is that important? Because I'd say that is some form of a starting material for making the continents. Be it the original continents were made from a mafic layer such as oceanic crust, or be it a mafic layer was subducted and that was melted to make continental crust. And in fact, there was a recent paper, sorry I can't remember the author of it, just recently come out and saying that continental crust is actually fundamentally built upon thickened oceanic crust. It came out earlier this year. Does anybody know the author of this paper? And that the thickened oceanic crust needed to be internally differentiated to make granites at the top, but this was activated by the convergent margin setting. I thought it was an interesting suggestion. It was in G cubed in about February of this year. I can find the reference. So I think actually Morb mantle is a fairly important reference frame. I did hear a comment this weekend. We don't need to study Morb anymore. But, it actually provides information set. It all depends. It's a reference perspective. I personally have a bias that it actually represents a fairly large volume. Some people, very few, actually tend to restrict it to the upper mantle. That is the top 28%. That is the region above 660 kilometers. I'm going to show that it's a residua from production of continental crust without question, but that the depleted mantle plus the continental crust may not equal the bulk silicate Earth. And it is definitely a recorder of convection efficiency. That last question that was being asked, the second last question being asked by DiPaolo and Hart. It's a very quiet group this morning. Okay, so Geochemistry showed at least that number up there. The Earth's surface heat flow is 46 plus or minus 3 terawatts at the 1 sigma level. Davies and Davies in 2010 came out with that number, 47 plus or minus 1. But the plus or minus 1 in that level really was the statistical uncertainty and not the systematic uncertainty that is associated with trying to parameterize all of the heat flow out of the surface of the Earth. My reference frame, I said the total radiogenic power in the Earth is 20 plus or minus 4 terawatts. Terawatts is 10 to the 12 watts. A useful number that I'll go back and forth on, 20 terawatts is equal to a compositional model for the Earth that has 20 parts per billion uranium. If we wanted, I will highlight that there are models out there for the silicate fraction of the Earth that goes from 10 parts per billion uranium, 20 parts per billion uranium, 30 parts per billion uranium. That's the same as saying it goes from 10 terawatts of radioactive power to 30 terawatts of radioactive power. It's an identical transformation because it just works out that way. It's very fortunate. And additionally, it's controlled by the fact that the thorium-uranium ratio of the Earth is 4, the chondritic ratio, and the potassium-uranium ratio of the Earth is 10 to the 4, the nominally observed ratio in ocean and continental rocks. Okay. Yes?
In this pie chart, where does magma move to the surface? It's conductive, right?
Not significant in terms of,
I would think that magma moving to the surface would be one of the most significant.
well, I mean, you can talk about it as the manifestation of the flux at the ridges.
Yeah.
Okay, in that sense, I guess that's what you mean, yes. But this is just sort of partitioning it into, if you will, the best way to look at this diagram is to say, I've put my hand on the outside of the blue sphere and turned the bright sunlight off. Okay, and it radiates 46 terawatts of power. What are the contributors? And essentially, you can divide them into two. One contributor is the radiogenic power, these two pieces of pie. The other contributor is the rest of the system. And it's best started for the students to just say the word, the rest of the system, the big unknown. And it is a big unknown.
For the in-ocean ridges, the structure of the ridge is such that the rising stuff is actually losing heat naturally, and that's the boundary condition for the plate model. So what you have is rising stuff, which is based in region, and it loses heat naturally, and this is then recorded in the Earth heat. But if you actually go for this, it's a storm.
I don't know how to turn it on.
It's at the bottom.
Here, I'll go find the other one. Oh, you got it on?
At the mid-ocean ridge is the structure of the axis of the ridge is such that the material that rises loses it laterally, and that's the boundary condition that you use for the plate model. It turns out that actually the amount of heat that's lost laterally is not a significant portion of the total heat lost to the oceans. It is maybe a percent or so. So it's allowed for the magma rising is indeed bringing heat, but that heat is lost sideways. So the only thing that's left is the fact that you know this hot material at the top, and then you have the surface heat flux. But because you're worrying only about the way the Earth loses heat, the only thing that matters is the heat that's lost at the upper surface. Whatever has gone on before then is irrelevant, and it's partitioned in between the plate and the rising column. So in terms of continental volcanoes, you got Yellowstone, etc. That's less than 1% total. It's huge, but there are a few Yellowstones and there are a few continental volcanoes. So we calculate that it's not a significant portion.
Claude, hang on to that for a second, because I'm going to just stir the pot a little bit more. And you're going to have to make a response, because I'm going to ask of you, please. So in large part, that number 46 or 47, you can hear it, right? Yeah. The number 46 or 47 is the thermal radiation from the Earth. Okay? Now, and as Claude says, you know, about half of it comes from the ocean, right?
Slightly more, yes.
Slightly more. And so it's a very important contributor. I mention that because, 5 or 7 years ago, Ann Hoffmeister and Bob Crist came out with a very controversial number. They said that all these other numbers, Chapman and Pollock, Joppa et al., Davies and Tavies, the numbers in the mid-40s were wrong. And they suggested that the heat flow from the Earth was actually 31 terawatts. Do you want to sort of give insight? 31.
I don't want to raise the dead from their graves, but okay. The main issue there was that it depends on whether you're using the heat flow that's recorded on the seafloor and the one that you estimate from the plate cooling. So when you measure heat flow through the ocean floor, you measure it by conduction. The only thing that you can measure is the conductive heat loss, the heat that's conducted along a temperature gradient. And that's what's measured by probes through deep sea sediments. And we all know there's hydrothermal convection, and that cannot possibly be accounted for by such measurements. So you're losing all the information about all this heat that's carried by fluids. If you account for these fluids, and this has been done both at the mid-ocean ridge, there are now detailed surveys of heat loss through a mid-ocean ridge flow, which shows that hydrothermal convection is really oozing out a lot of energy. And then you can go into specific areas where the sedimentation has been such that it has sealed off completely the hydrothermal convection. And there, the conductive heat loss actually matches the theoretical predictions. So the Hoffmeister and Crist model basically assumes that there is no hydrothermal convection, and hydrothermal convection does not contribute anything to the cooling of an oceanic plate, which I think sends marine geophysical people crazy.
Yeah. When I was much younger, I used to really sort of object to papers like Hoffmeister and Crist and go, they're crazy. But I actually find that it really challenges some of the dominant paradigms, and it really forced several of us to re-articulate what we believe are the informations that actually brought us to the conclusion of 46. And I actually find those to be at least for you, it should be at least far more educational, and it should unsettle you to say, is it 30 or is it mid-40s? And I think the question is completely resolved. It's in the mid-40s, not a number like 30. But it's very instructive. All right, so radiogenic power could be estimated to be 10 plus or minus 10 terawatts. My estimate of 20 plus or minus 4 is actually the uncertainty I had. The plus or minus 4 comes from the uncertainty I have on my compositional model for the Earth. The numbers that I gave you, 10 to 30, represent the range of information, the range of models out there competing for what would be the best estimate for the composition of the Earth in that system. So keep those numbers in mind as I continue to talk. So if we explain a portion of the pie, about 40%, by radioactive heat, then 60% is due to other circumstances, consequences. So it in part is due to the kinetic energy of accretion, which is incoming planetesimals or even present-day meteorites are coming in at 20 to 30 kilometers a second. And then we have 10 to the 24, 6 times 10 to the 24 kilograms of materials, and it ends up to a very large amount of joules in the Earth system. We actually do not know how that heat is dissipated, be it during the first week of accretion, let alone the first billion years. Okay, so that's a very large unknown. But as a consequence, we do not actually realize what is the dissipation rate over the last billion years. Estimates range from about 50 Kelvin per billion years to 150 Kelvin per billion years. I think the best piece of information we saw was when Ken Condi was showing us that we have a mantle potential temperature today of maybe 1350 in centigrade. And we have observations 2.5 billion years ago and before of commodioites that clearly came out of a hotter mantle. And I think that's the tightest constraint we have. The MG numbers I'm less persuaded by. The MG number translation into temperature is a good one, but the sampling is not sufficient enough to really constrain the delta T temperature with respect to the delta T time. Okay. Consequently, we have these two pieces of pie here. I'll just dismiss this one pretty quickly. Tidal dissipation, chemical differentiation such as crystallization of the inner core are minor contributors to this story. We have mantle cooling and core. This number is approximately 9, and numbers between 4 and 15 terawatts have been put forth. That number is simply determined by looking at the number of hotspots around the world, like Hawaii, Iceland, etc., Galapagos. Those would be the three biggies, if I remember it correctly. And you can estimate the thermal energy associated with those three areas as well as all of the other hotspot regions. You can do a calculation as to how much of that energy is the total surface energy budget. It's approximately 10%. And that system is believed to be transferring energy straight from the boundary layer, the core mantle boundary. And therefore, the expression of heat from the Earth's core through some translational loss in terms of convective upwelling in training, also ambient lower mantle, that number, actually 9 terawatts, is represented as the amount of energy being transferred from the core to the surface of the Earth manifested at ocean island basalts. Hence the significant range, factor of 3 in the heat flux from the core mantle boundary. Okay, so that's what we think that temperature boundary is telling us. And then if you take 7, 13, and 9 and subtract that from 46, you're left with 18 terawatts. And so that 18 terawatt number is really left over. That's all it is, simple subtraction. Don't get too proud. That's why it doesn't have a plus or minus. You can propagate it. But I actually leave it up there as informing us as to what is the energy in the mantle system. And it may not actually be all in the mantle system. It could still be some of it in the core. So that's the level at which we understand the energy budget. Please, computer, please back up. There. This diagram here shows time today, 4.5 billion years ago, the start of the Earth, power in terawatts. The black line is the total in the system. It ends here at 20 terawatts. the curves would be parallel to one another. I could have a curve here at 10 terawatts going up to here, and a curve here at 30 terawatts going up to there. Okay, so it depends on, you choose any model you want, and therefore you could see these different models for the Earth. But if we have 20 terawatts of energy today, we have over 100 terawatts of energy when we started the Earth system. This should be at least informing your intuition with respect to forming the continental crust in a Fife-like model between 4 and 4.5 billion years ago. Because the present-day crust has approximately half of the thermal energy of the system, the radioactive energy, sorry. And if 4.5 billion years ago, between 4.5 and 4 billion years ago, we took that power out of the mantle, we'd have a continental crust with 50 terawatts of power, approximately. It's an interesting result as a consequence. So I think that's a useful information set. We've gone through, just so you know, the nearly flat blue line, uranium-238. I've estimated that the concentration of uranium in the silicate Earth is 20 parts per billion. If you look back 4.5 billion years ago, it would be 40 parts per billion. The half-life for uranium is almost identical to the present-day age of the Earth. It's about 4.5 billion years. So we've used up half of our nuclear fuel, at least as far as uranium-238. As far as uranium-235, we've gone through 6 half-lives of uranium-235. We've really spent that fuel, even though it is the fuel that we often drive nuclear power plants with. Thorium-232, 14 billion year half-life, and so we've got a fair amount of thorium energy left inside the Earth. And potassium, as you can see, potassium used to be the most, the greatest contributor. And if you want some irrelevant piece of information, right at the Archean boundary there is when the power of potassium dropped below the 50% level. All right, in a simple scenario, primitive mantle. Somebody asked me about The Simpsons. I like to add The Simpsons because it was being a parent. My son just turned 21 when I was here. He introduced me to The Simpsons, and they've kept my science at a useful level. The primitive mantle is often also referred to as the bulk silicate Earth, that is, the material that surrounds the Earth's core, if you will. And in large part, it actually contains information and materials that are of considerable interest to us. And so with that starting scenario, I tend to say that the modern mantle, this is a thin section, plus the crust. And I didn't say continental crust because I used both of the oceanic crust and continental crust equals the primitive mantle or the bulk silicate Earth. Okay. So I get a little schizophrenic because every once in a while I'll talk about the oceanic crust, but at the same time I consider the oceanic crust such a transitory visitor to the top of the Earth that at other times I consider it part of the mantle, strictly speaking. So we'll look at the mid-ocean ridge basalt source region or the oceanic crust right now. Okay, complementarity compositional nature of the continental crust and mid-ocean ridge basalts. Parentheses, afterthought, and ocean island basalts. So at some level, I'm in the literature for both saying the continental crust and the ocean and the mantle, if you will, or the oceanic crust source region, are complementary in nature. That if you add the two of them together, you'll get to the silicate Earth. I'm also in the literature for saying that doesn't happen, and in particular, I'll show you why in a second. But if we look at just these elements, the rare earth elements, these elements here are presented in this fashion because they sit down at the bottom of the periodic table. Nobody handed in their periodic table questions. Maybe we should collect them afterwards. Also, I'm very pleased that somebody signed their name, and he's not here, Francis Alberid. So if you get sort of unsettled, put your name on the piece of paper as somebody else. Cinti Lee would be a good name. We use diagrams like that because we actually like non-dimensional data too, and these are the abundances of the rare earth elements in the rock divided by the abundances in a reference material. It could be the continental crust, it could be the primitive mantle, or it could be chondrites. In this case, it was chondrites used as the reference frame, and that just takes out the odd-even abundance differences. What you can see in red and green are estimates of the global MORB composition and what might be a nominal N-MORB composition. And what you can see in the solid triangles is Rudnick and Gauss continental crust composition. And if you take the mass fraction of continental crust plus some estimate of what the source region of this would be, you should come out to the primitive mantle composition. And what you can see here is the very slight depletion in the light rare earths found in the mid-ocean ridge basalt source region, and a very strongly enriched light rare earth pattern in the continental crust. Now, I use this diagram because I like the way it kind of twists my mind. I look at it and I go, those two aren't complementary. Well, in fact, they can be, very much can be, because this is a 0.5% by mass, the continental crust is, of the silicate earth. Okay? So it's actually strongly enriched, but really very small volume. Okay? To put it in perspective, the total amount of lanthanum that sits in the continental crust is only about 15% of the budget. So, it's like the end of the year, and I've done stock, and I've done the inventory. And at the end of my effort, I've concluded that just about 15% of the lanthanum in the planet is in the crust, and that's it. So, really, in that normalization factor, this triangle plus either the red or the green dot can be added together, and you could have a complementary pattern. Okay? So they could be made to look like the bulk silicate earth, and I actually tend to think that that's a very consistent argument. Yes? Truly insignificant in mass fraction. Truly insignificant. But the smaller degrees of partial melting you can actually make Hawaiian basalts from a slightly depleted, light earth depleted source region by very small degrees of partial melting. We recognize it as a source in the mantle, and we're really, really hard-pressed, although that didn't stop us from Arevalo, myself, and a few others publishing a paper earlier this year, characterizing what is the mass fraction and abundances of elements in the Ocean Island basalt source region. Okay? But we're very hard-pressed, and we do believe that source region to be order 20%, but there is considerable uncertainty in that number. By the way, if we made it 20%, it's very dilute. That is, it's not strongly light rare earth enriched. If we make it 1%, such as it might be the volume of the LLSVPs, then that actually has a very high concentration of trace elements to make partial melting models work. And that's what I'll be talking about, is partial melting models. And so whenever you talk about domains in the mantle, if they tend to be very small, 1% maybe, then you really must have them strongly enriched. And having them strongly enriched means they have lots of uranium, lots of thorium, lots of potassium. They could become thermally unstable at depth in the Earth's interior. All right, just a few words of information about elements. Well, I just ever so briefly refer to incompatible elements. I could have started out with this diagram earliest because really if we're talking about the incompatible elements, thorium, uranium, and potassium sit over here. These are part of the highly incompatible elements. These have partition coefficients between the crystal and the residual crystals in the melt. That is order 0.01. That is, they get enriched in the magmas, maybe as much as a factor of 10 to 100. Oh yeah, I changed this slide. Another slide not saved. I should have stayed in bed. That's what I should have. The highly incompatible elements are really very, very useful to the geochemist. And because they effectively remove melt from the mantle, they are effectively removed from the mantle by melting. We tend to think of melting in terms of the Earth's mantle as being somewhere where about 1% partial melting to 10% partial melting, maybe 15%. Typically, often scales, we like 5 to 10% partial melting. We can solve the equations mathematically by using less degrees of partial melting, but there are penalties that sometimes we don't embrace. And in particular, I'll show you in the next couple of diagrams the see-through. That is, from the lavas, we can estimate abundances of elements in the mantle below. So if they have transported from a source region that's 50 or 100 kilometers down, we can actually make coherent stories about what's down there. And in particular, we have quite a range. We call some elements high field strength elements, and we call some other elements large ion lithophile elements. So in the case of high field strength, elements like thorium and uranium behave very much like potassium. Potassium, thorium, uranium during partial melting behave very, very differently. And potassium would plot right there too. Potassium is a 1+ cation. It's on the far left side of the periodic table, so therefore it has one electron in its outermost s orbital. Whereas thorium and uranium are typically 4+ in the Earth's mantle, and that means they're really ready to share 4 electrons, both in the 2 outer s orbitals and the f orbitals, more than likely. And in that case, we are really talking about elements that should behave entirely different than potassium, given the electronic structure. But we observe that the highly incompatible elements, be it they have a high field strength in terms of electron orbital sharing capacity, or they're just large ion lithophiles that's just really referring to the 1+ cations, they can behave very similar, and collectively they'll inform us about the Earth's mantle. And these others that we call only moderately incompatible, they also have another usefulness. I think Matt Jackson and Mark Jelinek just had an interesting paper on estimating the composition of the Earth's mantle system, and they actually focused on ytterbium and lutetium because, in fact, there's not a large amount of variation. You can see here, this is the data compilation by Rico Revelo and myself and Mario Luong. That bandwidth there is really due to small differences in the degree of partial melting, but larger differences in fractional crystallization. So there were, for the global MORB compilation, we had over 700 mid-ocean ridge basalt data. So you can see a large amount of that, hundreds of data points presented here. And actually we can collapse this down to less than half of this for the ones that have relatively high MgO contents. And so really, we have good ways to estimate the amount of lutetium in the Earth's mantle. And that's useful. In terms of the continental crust, there's only a couple % of lutetium wrapped up in the continents. The rest of it's in the mantle. So in fact, when doing the math on the system, we really don't care. That's what we'd consider uncertainty in the system when we talk about the lutetium budget for the Earth. The continents are not important. Yes, Matthew.
Sorry, how do you explain the fact that on the left side you have more differences in your samples?
Okay, good question. So 1 to 2 orders of magnitude on this side, factor of 5 on that side, and that really is due to the melting. And I'm going to show that in a minute, but it's really these elements here are highly incompatible and readily partitioned. That is, they have, well, let me go and show you the distribution coefficients. It's right here. Oh, yeah, and I had words down here about fractional melting. Okay, so non-modal batch melting. We'll often invoke a batch melting scenario, and the first word here, non-modal, really if I had D naught there and I had D there, it would be about the same as this equation. But P, really, the P parameter in this is really the fractional mode contributing to the melt. So let me just deal with this. The concentration of element in the melt, so that was the mid-ocean ridge basalt, divided by the initial concentration of the element in the source. What is the concentration of that element in the mantle? So if you have 100 parts per billion uranium in the lava, you might have had something like 5 or 10 parts per billion uranium in the mantle below. Okay. So for uranium, that's what that factor would be. Okay. And then this D naught F and 1 minus P. D naught is the bulk distribution coefficient. I'll get to the distribution coefficient in a second. And F is the fraction melting, 5-10% partial melting. Okay. So this is actually the mathematical relationship, or one of a mathematical relationship that really is informing us as to what is the abundance of elements down in the mantle. And as I said, you can treat it as the non-modal P, because the mantle phase is in the upper mantle. There's a lot of agreement about the nature and composition of the upper mantle. It is about half of it's olivine, 20 and 20% of clinopyroxene and orthopyroxene, and a little bit of spinel. And that would be in the top few the top few tens of kilometers of the Earth's mantle. From about 30 kilometers to 60 kilometers, the stable aluminum phase is spinel. Beneath that, the stable aluminum phase is garnet, and you can see that these numbers change around. Okay, so that phase changes end up going to be redistributing the major oxides, and it will also redistribute some of the trace elements. Okay. If you melt this portion of the mantle, you get a very large contribution from clinopyroxene. You melt this portion of the mantle, you get a very large contribution from both clinopyroxene and garnet. You get a little bit less so orthopyroxene during the melting, and in fact you produce more olivine in the mantle as a result of melting. So the mode, this fractional mode contribution is actually, we used to do it as simply what are the modes down there, but once we've done the calculation in a more petrologically useful way, we actually end up, and we knew this, you end up making olivine in the mantle during the melting scenario. So in some sense, the concentration of the liquid over the initial, for incompatible elements, it's much greater than 1. So for the elements, it should be this way. Oh, no, the wrong way. So these are the elements much greater than 1. The CL over CO, the CL over CO is maybe a factor of 10 to 100. Okay, those elements, the factor is only a couple. Yes.
What's the transition depth between those two kinds of metals?
Between those two mineralogies?
Yeah, is there any kind of seismological?
Seismologically, I don't believe it's visible. And the depth, there is a plagic clays leurzolite to spinel leurzolite that occurs at about 1 GPa, right, Chip?
Well, the spinel garnet is going to be more.
Right, 2.5 to or so, or 3 GPa, but the first one is around 10 GPa, 1 GPa. Yeah, yeah. So I do not believe that either the plage to spinel or spinel to garnet phase transition has ever been seismologically imaged. Maybe it has. Here we go.
I mean, sometimes people will refer to the Hales discontinuity as possibly being caused by that phase transition. The Hales discontinuity is kind of wherever you want it to be, as long as you have a seismic discontinuity.
Great. Yeah, at about 2.5 GPa in a leurzolitic composition would be the phase transition from spinel peridotite to the garnet peridotite, and it gets a bit deeper in more melt-depleted compositions.
It's a transition, so it's
Yeah, it's not sharp like the 410.
The other thing too is that at high pressure, in the presence of garnet, the reaction relationship is actually orthopyroxene producing. So that changes Mike Walter's experiments and others. So at low pressure, that's correct in producing olivine.
Right. Okay, and so I want you to pay attention to this difference here. So this would be saying the concentration of the element in the liquid over the mantle source region. But when we talk about D values, it is described as the concentration in the crystal divided by the concentration in the liquid. So that goes to less than 1. So this is a little bit confusing, but I wanted to do it that way so that you'd understand the relationship, D values. Now I can show you D values. So here's that other relationship. This is modal melting. Cl over Co is equal to 1 over D, F1 minus D. So that's, you use D twice there instead of D and P. I can tell you for batch melting, non-modal melting, and also fractional melting virtually give you the same curves for very low D values. These very, very low D values you can't distinguish on this diagram. Okay? So the concentration in the liquid over the initial concentration, 1, 10, 100, goes up rapidly at low degrees of partial melting for very incompatible elements, the highly incompatible elements. The moderately incompatible elements, they might have a D of 0.1, something like lutetium has a D of about 0.2, and so its curve would go along here like that. Okay. I won't talk about, this is the residue, and for partial melting and at say 10%, what you can see is that the residue is quickly and strongly depleted in the concentration of uranium and thorium and potassium as a result of just taking a little bit of melt out. Okay.
It might be worth pointing out to the students that those equations are slightly complicated. It's real simple if you think about the really incompatible elements, because those D's go to 0. So the concentration of the liquid over the mantle is just 1 over F.
Mm-hmm. So I said I would talk about the complementarity, and so this is an interesting, a 2% partial melt, a source that's flat, and what's the residue. So just using those equations there, what you end up getting is a 2% partial melting of a primitive mantle puts you up here. This is 10, that's about 60. The continental crust would be sitting slightly there, so you could dampen it down a little bit. And this source region, that is what's left behind in the mantle, well, this looks like continental crust, and this looks like the mid-ocean ridge basalt source region. And, I've been standing here waiting for my thing to come in. That was another thing. So I had a beautiful circle that went around here, and it said, niobium is important. And the reason niobium is important is because niobium is one of those key elements that tells us that the complementarity between the continental crust and the mantle source region for mid-ocean ridge basalts is not there. Okay? There's not a straightforward complementarity between the two. And in fact, we use this depletion in niobium to often say, to essentially be the smoking gun, the fingerprint, the DNA signature that said continents were created in convergent margin settings. Because it's in the convergent margin settings that we have a robust and simple and reproducible, happens every time, method by which we hold niobium back during the partial melting or melt generation event, and that the continental crust is enriched in all of these elements but not niobium, not tantalum and other details, but that's an important parameter observation, and it actually weakens the model that says you take the continental crust plus the depleted mantle and you have the primitive mantle. So there are devils in these details that you cannot take the primitive mantle, partially melt it by a little bit, create the continents, and create the residual mantle. That's not the entire system. There's more that goes on. Okay. Now for some details about melting again. Fractional modal melting, in many ways, it can be thought of as good enough. This is modal melting, but at the fractional level. And really what I'm going to try and do is actually bring you through, in a quick step-by-step fashion, really how we look at element and element ratios in the Earth's mantle. I know that for the geophysical community, there's a large amount of element ratio space out there that the geochemists use. I won't apologize for all of the geochemists. Some of them absolutely drive me crazy. And if I'm driven crazy, I know geophysicists can't understand why did they plot polonium-bolonium ratios. It can be atrocious out there sometimes. But I hope to give you a geochemical rationale over these next 3 slides as to why these ratios are done the way they are. Again, here we have the fractional modal melting equation from Shaw 1970, and I actually labeled the other ones. They're all from Shaw 1970, my other diagrams. F can be thought of as 0.1, 10% partial melting. It's a really handy way to look at the system, and so it makes all the math really quite easy for the moment. Concentration in the liquid over the initial, so that's the liquid. There's the concentration initial. That's actually an easy way to deal with it. And then the distribution coefficient for the element I, it's a solid liquid partitioning. So the bulk distribution coefficient is the sum of all the distribution coefficients. You can talk about the individual, like the partitioning of elements between melt and clinopyroxene, melt and garnet, melt and olivine. Or you can sum up their relative contributions as they add to the melting of the mantle. Okay, but I'm going to look at I and J. So the concentration of I in the mid-ocean ridge basalt relative to the concentration of J in the mid-ocean ridge basalt. And this equation shown here really can tell us if these two are related. You didn't show up on my screen. Thank you. Okay, so if the solid liquid distribution coefficient for I is approximately equal to the solid liquid distribution for J, then, and in this, we're talking about the mid-ocean ridge lava composition, and DMM, the depleted mob mantle. That's the depleted mantle. And what we're really trying to do is get to a depleted mantle composition. We have these two parameters here, and if we have this scenario, then the concentration of I in mob divided by the concentration of J in mob is equal to the concentration in the mantle source region. And that becomes very, very useful. A tiny bit of rearranging of elements, but really what I want to come down to is going from the log concentration of I in mob is equal to the log concentration in the source region minus the melt fraction and corrected for the melt fraction times the raised to the distribution coefficient value here. You rearrange this equation and you come down with a essentially a description of a line on a diagram. The concentration of I in the mid-ocean source region can be also expressed in terms of J because this equation and this equation has I and J. And from the previous equation, we can show you that we can relate these two if their D values are equal. So the concentration that we can measure readily in the lava is equal to the concentration in the lava relative to the ratio in the source region. So the concentration of J, the concentration of I, the slope for a D value between DI and DJ being equals, this slope is actually giving you the concentration in that source region. And what's important is really at low values of F, i.e. 0.1, 0.05, something like that, we can be pretty assured that these concentrations are faithful recorders of what's down there. And thus we can start looking at potassium versus uranium or strange elements like titanium and europium. I remember one time, it was around 1987, I gave a talk at a meeting. And I talked about the titanium-europium ratio. And in fact, it was all related to understanding the nature of titanium depletion in the mantle. A lot of discussion going on at that time. Francis Alberib was in the audience at the time. And he just started laughing. And I can't blame him for laughing. Who in their right mind would take an element titanium divided by an element europium? It's intuitively to a geochemist, you go, doesn't make any sense. Doesn't make any sense. However, what's really important is log J, log I for this kind of consideration shows you log Ti, log europium, the slope is 0.97 plus or minus 0.07. That's uncertainty is at the 2 sigma level. That says that they actually behave perfectly like each other. Very, very strange element pair to actually say behave perfectly like each other. They behave perfectly like each other because there are not phases that suck out titanium, such as titanomagnetite, and there are not phases like plagioclase that suck out europium. Okay, but when you come up with a wacko ratio, the titanium-europium ratio, the relationship is really based upon the fact that you see these observations and they're behaving, they're melting out of the mantle at the same rate. Okay, that doesn't say that's happening in the island arc setting, but it does say it in the ocean island in the mid-ocean ridge basalt source region. So in fact, I can relate a major element, titanium oxide, to a trace element, europium. There are a few thousand parts per million. Well, actually, the standard basalt in Hawaii is 4% TiO2, and the standard mid-ocean ridge basalt is between 1 and 2 weight percent TiO2. A major element oxide. The concentration of europium, about 1 part per million. So orders of magnitude difference in concentration, you can actually relate these two elements, and it makes good sense that it can be justified mathematically. Two elements like potassium and uranium are also correlated. However, I can tell you that because M does not equal 1, even at the 2 sigma level, I can tell you that those two elements actually do fractionate from one another during the melting process. Oh, yes. Now, this diagram is actually what we went in and did a fair amount of information on really a lot of elements. This is the first two then barium, thorium, two highly incompatible elements. But in fact, you can see the slope is 1.19 plus or minus 0.03. Again, confirming what we had already known intuitively, that your question was the elements on the far left. Barium is the one that really shows the greatest variability in mid-ocean ridge basalts. More variability than thorium. And the slope here, M, 1.2, it is actually approximately, you can think of it as 20% more incompatible than thorium. Barium is about 20% more incompatible. They're both highly incompatible. Okay, it's the number 20% is wrong, but it gives you that sense. Okay, the intercept's not that significant. Okay, here you can see that two elements. Where does hafnium sit on the periodic table with respect to zirconium? Anybody know? Right. Okay. So in fact, a geochemist might have intuited this kind of relationship, because if you look at the periodic table, titanium, right below titanium is zirconium. Right below zirconium is hafnium. And in fact, zirconium-hafnium is very difficult to fractionate in the Earth. Even zircons, a mineral that has zirconium silicate, has hafnium at the ratio zirconium to hafnium of 40. That's a ratio of 40. Okay, so these two elements actually follow one another, and it emphasizes why the periodic table is your friend. For those of you who just arrived, I gave a tutorial on the first Tuesday, and my starting point was a blank periodic table to be filled in. I use it all the time, the periodic table. And what you can see here is there's a small difference in the partitioning. Yttrium-holmium is another element. Yttrium is below scandium on the periodic table, and below yttrium is actually that missing space for the lanthanides, or the lanthanoids as they should be probably called. And it turns out that the best fit for, where is it? Yttrium is holmium, 1.01 plus or minus 0.04. And it's actually the best fit when you look at the radius. Okay. So these details in geochemistry are really the points I wanted to get across in terms of some of the basics of geochemical information. They get applied here, where we're trying to understand the concentration of uranium in the oceanic crust, trying to understand the budget of uranium, trying to understand the recycling of uranium. So you go to the inset here. This is the inset. And what you can see is marine sediments might have several parts per million. Altered oceanic crust can have a factor of 5 more uranium than the fresh basalt. The fresh basalt might start off with, I do know the global MORB fresh mid-ocean ridge basalt value for uranium is 80 parts per billion. That's just what you tend to find. The uncertainty on that, or the variances in that population, only around 15 parts per billion. Okay. But if you alter it by ocean crust alteration products, you jack up that number by a factor of 5 at a minimum. And you sprinkle a little bit of dirt from the continents, and you jack it up even more so. So this is useful information for informing us as to what goes down the trench and what might be involved in the genesis of island arc magmas. Okay. But nonetheless, a very powerful observation was made in 1963 by Wasserberg and colleagues that the ocean floor lavas have a potassium-uranium ratio around 10 to the 4. And at the same time, he had observed in that same article that granites, rocks from the continents, have a ratio of 10 to the 4. So amazing is that no matter what has happened in terms of differentiation, these two elements have remained relatively fixed to one another. Okay. That is, the potassium-uranium ratio of a mid-ocean ridge lava, 10 to the 4, is the same as in the continents, and our intuition drives us to say the potassium-uranium ratio in the mantle is 10 to the 4. Why is that important? Because you'd like to say what the potassium to uranium ratio in the planet is. Uranium, I will go to that in a minute, is a refractory element. Can be fixed by chondritic ratios. Potassium is a volatile element. Can be spread all over the place. We just have to start guessing what is the volatile inventory of the planet. Okay, so that's important. The thorium-uranium ratio is around 3. The chondritic ratio is around 4. The continental crust ratio is a little bit higher than 4. We know it to be about 4.5 to 4.8. So the continents actually don't deviate grossly in terms of the amount of thorium-uranium in them. There are indeed uranium deposits that are almost free of thorium. They're crackerjack full amounts of uranium. But when you do a regional survey of the average continental crust, you still come up with a ratio of thorium to uranium of a little over 4. And in fact, if you go a step further and look at the lead isotopic information, the 208 star 206 star ratio, where the star refers to the amount of radiogenic 208 that was produced during the decay of uranium to lead, and that equivalent decayed from, thorium-232 decays to lead-208, and uranium-238 decays to lead-206. And if you look at the amount accumulated in the continental crust, that ratio remains very close to 4. It's just greater than 4. If you look at that same ratio in the oceanic environment, it's called the kappa value. It also is very close to 4. And it tells you that in the Earth system, in terms of differentiation, we've not had, in terms of radioactive elements that are producing heat, significant fractionation during the generation of the continents of uranium from thorium from potassium. Okay. So that's actually very, very useful. And the other thing we can see in this diagram, you really can't see it, is right here, the estimate for the amount of uranium in the mid-ocean ridge basalt source region is order factor of 10 less than in the crust, factor of 10. So if it's 80 parts per billion in the crust, in the fresh crust, it must be 8 parts per billion in the depleted mantle. The best estimates are running between 3 and 8. We don't really know what the value is. But there are penalties that are paid for depending upon the amount of radioactive power in the source region. Many geochemists will become uncomfortable making it a lot less than 3 parts per billion, and some get very uncomfortable making it more than 8 parts per billion. But if you make it more than 8 parts per billion, there are other penalties. So we tend to only know a limit to which these elements are in the mantle. So for me, and I had a nice thing that would come across here at this time. This is my window into the mantle. That is, the oceanic crust is less than a couple 100 million years old. And it really tells me a lot about what's down in the mantle today. The continental crust is much, much older, and we've talked a lot about it this week. And in particular, I'm not going to cover the composition of the continental crust, because that was covered by Roberta, nor the lithospheric mantle attached to it, because that will be covered by Rick Carlson. Okay? There's been a sufficient amount. So I'm now just going to finish ever so briefly on really talking about the models for the Earth. As I said, it's schizophrenic, so this is where I make my transition. I'll ever so briefly, hopefully, unsettle you. Okay, how do we get it, and how well is it known? The models must be realistic and multiply constrained. And in fact, whenever a geochemist does this, they really need to do a reality check. And the reality check for the geochemist is the geophysics. It starts out with PREM, the 1D seismological description of the Earth. Okay. The constraints really come from geochemistry, cosmic chemistry, petrology. Okay, I'm biased, so I put it on this side. But they have to really match geodesy, seismology, and mineral physics. And because I can't not say it, I have to also say neutrino geophysics. And if you beg me, I will tell you something. I'm particularly driven to ask the question, what were the conditions in terms of pressure, temperature, and FO2 versus time at 1 astronomical unit out from the sun? That's where we are. And in fact, a lot of times what I'm involved in doing is describing the product, not the process. The product is the Earth, and the real question is, how did it get to that composition? And that, for me, is really the exciting thing. Because it wasn't touched upon, I'll just briefly say how we assembled the body and where the big questions are. So what was the composition of the Earth and where did the stuff come from? Ever so briefly, 4.5 billion years ago, we had a supernova. We might have had a family of supernovae, that is, stellar explosions. We do not have that constraint. We do have observations that there are families of supernovas that happen in clusters. The energy and some amount of mass from that supernova was imparted into an interstellar gas dust cloud. And it probably only captured some of it and imparted a spin momentum and this rotation into later the fraction of the ISM that was captured by a supernova explosion was essentially led to the formation of our solar system. Abundant amount of evidence from people like Rick Carlson and many other scientists actually helped to underpin exactly what happened in those earliest days. And for many elements and many isotope systems, we see homogeneity. That means that if I go and look at the zirconium isotopic composition of anything on the Earth and anything of any meteorite, I will see the same isotope abundances. That doesn't mean if we went to planets 15 stars away, we would see those same isotopic abundances. That came from a different supernova explosion. But we typically know that the abundance of lithium-7 is 12 times the abundance of lithium-6 on this planet. But we know it can be fractionated by processes. And we know that the abundance of zirconium-90 is about twice that of zirconium-91. So, in fact, it's a very powerful observation. There is homogeneity. However, we do know that there's heterogeneity in the isotopic abundances of some elements. And we're actually moving to a point where we can actually talk about isotopic heterogeneity in the solar system 4.5 billion years ago. The standard model for making planets is really described here. And I quotation mark the standard model because I'm going to give you some insights that says I'm going to shake this up in a way I didn't like. I never thought this was going to be possible a few years ago. So orbital and seismic data, and when I say orbital, geodesy data, really have to be a very major point of constraining our models. I'd say that the chondrites are primitive meteorites. Chondrites are really those rocks from the solar system that are left over from action happened 4.5 billion years ago, and that's it. And they're an intimate mixture of rock and metal. Now, we're not so intimate. All of our metal is in the gravitationally stable center portion of the Earth, and then the rock is on the outside. Okay, so chondrites are actually the pre-differentiated building blocks that make up the Earth. Okay. So too the composition of the solar photosphere. I will show you an image of the solar photosphere and its composition. It's an important bounding condition. Refractory elements are in chondritic proportions. That sentence, refractory elements in chondritic proportion, used to be immutable. That has to be changed. And we have to ask ourselves, did we accrete pre-differentiated planetesimals that did not have all of the refractory elements in chondritic proportion. That's the one that really shakes me up right now. The absolute abundance is model dependent. How much thorium, how much uranium is really about my model versus your model. So I've said 3 models, 10, 20, 30 parts per billion uranium. That's where the competition is right now, and it's up to you to make these kind of decisions as to what is the best logic train I should be working with. The big elements, magnesium, iron, silicon, and oxygen, are non-refractory. Anybody's guess. I'm going to restrict it to the first 4 rows. Would anybody guess for me how much the Earth is described by magnesium, silicon, oxygen, and iron? What is the mass fraction of the Earth made up of those 4 elements? I'm not going anywhere until I get somebody to give me an answer in these first 4 rows. I know that. How much mass is described by those 4 elements for the whole body planet? Give me a number, not an adjective. Huh? 99. 93. Impressive. Everything else is trivia. These 3 elements, we still struggle to actually constrain those. They make up 93% the mass of the Earth. And that number is constrained within 0.5%, really. There are chemical gradients in the solar system. It is exceptionally important to remember that the rocky planets and the gas planets are grossly different, and they're both planets. Okay, so that tells you that the distribution of volatiles, and I use the word volatiles very different than you probably intuit volatiles. You think of volatiles as water, CO2, etc. No, to me, volatiles are lithium, sodium, potassium, rubidium, cesium, because they're not refractory elements that I referred to there. They're nitrogen, carbon, oxygen, but lead is a very volatile element. Zinc is a volatile element. So when I talk about volatile elements, I'm talking about volatile elements in the early solar system setting. The non-refractory elements are very model dependent. So thorium and uranium are refractory elements, whereas potassium is a moderately volatile element, and that's where the guesswork begins. So it's worth at least seeing meteorites. In the red box here are the chondrites, and this is a one type of chondrite. Hey, get back there. Oh, my heavens. I don't know. This is an undifferentiated planet material here. This is an iron meteorite. They're pieces of some sort of metallic core of a differentiated body. This is an achondrite. It's a calcium poor diogenite, mantle crust piece, if you will. Okay. So we have beautiful examples in our meteorite collection. And in fact, some people would even say that these pallasites, which is olivine and iron mixture, might represent co-mantle boundaries of planetesimals. Yeah, at some level. But at some level, they're products of really a car accident between 2 meteorites. Let me get the reference frame meteorites ready for you. I will tell you in a couple minutes that enstatite chondrite model for the Earth is pretty nifty. Enstatite chondrites represent 2% of the 1,100 meteorites that have fallen to the Earth over the last 1,100 years. 1,100 meteorites, 1,100 years, 2%. They might not be represented. Now, the other important part of this diagram is most meteorites that we study, not just the falls, but all of them, fell to the Earth 500,000 years ago or less. The most important piece of information you take away from this diagram is our reference frame is really biased, skewed to the extreme, and we don't even know how much it's skewed. My overarching statement I make here, and I've made in my own articles, is that meteorites are simply a guide, and I think it's foolhardy to say, I must fit the Earth to this kind of meteorite. Okay? Meteorites are simply a guide, but they are the best guide for our building blocks. So, in terms of continuous absorption and emission spectroscopy, I remind us all that we actually can look at the absorption spectra associated by this simple diagram here for the sun. Here's the absorption spectra for the sun, 50 lines of data, going from the near infrared to the ultraviolet. We then get that, and it becomes plotted on this axis as an abundance normalized to 10 to the 6 atoms of silicon. We just assume in the spectrum 10 to the 6 atoms of silicon. You can see there's a lot more atoms of hydrogen. Okay? And we get a meteorite, we bring it into our laboratory, and measure the heck out of it. And when we do this for C1 carbonaceous chondrites, we find this absolutely phenomenal one-to-one relationship over about 7 orders of magnitude. This is an important diagram. This says basically we can hold a piece of rock that has a compositional match to the sun. And for those of you who don't know it, the sun is 1,000,000 times more massive than the Earth and 1,000 times more massive than Jupiter. So every planet out there added up means nothing relative to the mass of the sun. But we can hold a 3-kilogram rock in our hand and it matches the sun over that many orders of magnitude. So that's an important, powerful observation. Now we can go a step further and look at, roughly speaking, all the chondrites. So this is CM, CO, CV, varieties of carbonaceous chondrite. Okay, and so always we will have the photosphere versus the rock. These are the ordinary chondrites. And these two here are the enstatite chondrites. And then over here is my best estimate for the composition of the silicate Earth. So we look a lot like the sun, but the devil is in the details, and you can see the volatile elements off to the side here. When I've been talking about volatile elements, I have to say there's a twofold classification of elements. Refractory, those that condense out of a nebula at greater than 1400 Kelvin. Moderately volatile between 1250 and 650. There are rationales as to why we actually cut it off there. And then the volatiles, the ones that you would think volatile, like CO2, nitrogen, carbon and oxygen. The ices that will make up methane, water, CO2 ice, ammonia, etc. Then we also classify elements according to this scenario: siderophile, lithophile, chalcophile, having affinities to iron, oxygen, or sulfur, stored in the core, mostly in the mantle, and some in the core and some in the mantle. Okay. This is actually then showing you the lithophile elements. This would be the bulk silicate Earth. This is the siderophile elements, and these would be the elements in there. So estimating the bulk Earth composition really comes down to this. Must be consistent with PREM, the seismological model. Check models with experimental mineral physics data. That is, I will just ever so briefly show one diagram that didn't get incorporated, dang it all. You'd like to know that a mass balance of the continental crust plus the depleted mantle plus the ocean island mantle equals the silicate Earth. And there are questions as to whether or not that's the example. I've used periddotites plus meteorites to make the Earth, but I still ask which meteorites. The isotopic composition of meteorites is really giving us conflicting pieces of information. Then you can use meteorites only to drive the composition. And again, the isotopic composition of meteorites is driving me crazy. It's extremely useful. But sometimes we have matches, but if you look at all of them, we don't always have matches. So it's that mismatch that is really driving us. Assume non-chondritic models for the Earth. Oh boy, does that make me uncomfortable. Well, a couple of years ago, Hugh O'Neill and Herbert Palme come out with what's called the collisional erosion model. It was to explain Boyett and Carlson's 142 neodymium model. Neodymium observations. They had measured that the isotopic composition of neodymium in the meteorites didn't match that for the Earth. Disconnect. If we force the Earth to look like this meteorite, then we have to have a balance in the system. We have a hidden reservoir deep in the Earth, or in this scenario, we lost it to space. Okay. Now here's where we sit. This is an important piece of education. Earth models update, and it's not just last year. I even corrected that this morning. Murakami, May 2012, Nature. The lower mantle is enriched in silicon. consistent with the C1 chondrite. That's not my model. The C1 chondrite model has too much silica, therefore it has negligible amounts of olivine in the lower mantle. Ian Campbell and Hugh O'Neill, Nature, same journal, a couple of months before. Evidence against the chondritic Earth. One of them is wrong. Possibly both of them are wrong. If you've heard people talk about McDonough and Son, I don't agree with either of those models. Okay? But I can swear to you that one of them's wrong. Zhang et al. The titanium isotopic composition of the Earth and Moon overlap with that of instantite chondrite. Fitoussi and Bourdon says silicon isotope supports the conclusion that the Earth was not built solely from instantite chondrites. Well, at least this was published in Science, so that journal is not inconsistent. And then in EPSL, Warren says, among the known chondrites groups, the high ion instantite chondrites yields a relatively close fit to the stable isotopic composition of the Earth. This is some valid work. This is experimental mineral physics. They have a result. They match it to Prem. I don't like it. There's shortcomings, but it's out there. This was explaining the 142 data, but this ends up having an Earth with 10 parts per billion uranium. That means the mantle has only about 3 terawatts of radioactive power. I don't know if you feel uncomfortable driving the Earth's engine with that little fuel left in the tank. So, as I conclude here, compositional models differ widely and imply a factor of 3 difference in the thorium-uranium content of the Earth. I'll just leave this up and I'll let you ask me questions. I left that up there because it's a ternary diagram of major elements that shows you your answer to the question, 93%. And my Earth doesn't sit inside the field defined by meteorites. That's it.
Well, we have time for some questions.
Go for it.
What's the mechanism that holds niobium back from going into continental crust?
I don't know. But I can tell you I've speculated on the topic. I won't claim to be a petrologist, but in fact, I do know that you can produce rutile in a subducting slab, and that if rutile's there, it should hold niobium. And some people will say that the niobium-tantalum fractionation seen in the continental crust is not consistent with rutile holding the niobium back. Good. Just find another phase that's involved in the generation of magmatism at the convergent margin that holds niobium back because it's observed at that environment tectonically. So I'm comfortable with rutile, but that's a debate still in the petrology community. Cool off.
More questions?
Yes.
So if the continents and the depleted mantle add up to the BSE...
Almost BSE.
Yeah, so what is the role of the lithospheric mantle under the continents in the balance of things?
Okay, so that's a great segue question into Rick Carlson's talk, which will be on tomorrow. There you go. I've been involved in examining the question. So part of this question leads right back to niobium. And I know that some people have asserted that there is a niobium-rich reservoir in the lithospheric mantle. The first thing I would say is no. I find no evidence for that. Secondly, I've put in an effort to try and characterize what is the abundance of elements in the lithospheric mantle. I've also put in some effort to actually describe how much lithospheric mantle there is. And the mass fraction of lithospheric mantle is fairly difficult to actually finger point or pin down, because that really depends upon the seismological community giving us better and better and better insights into what might be the LAB. The LAB being defined as the base of the lithospheric mantle. And then we can actually define its mass fraction. If the mass fraction is, as best as we can guess it, something like 2 to 3 times the mass fraction of the continents. So the continents are represented about 2 times 10 to the 22 kilograms, or 0.5% of the silicate Earth. You might say that the lithospheric mantle is between 2% or 3% of the silicate Earth. Not well pinned down. It really depends upon how thick you make that lithospheric mantle, and it's clearly observed by all of our data sets that it's thin in some places and thicker in other places. The next thing you want to do is assign a concentration of elements, and the best you can do is look at a large number of mantle xenoliths, look at a large number of massif peridotites, do statistics on it, use the median, please, don't use the average, and it will describe it. And it really is a truly, I believe in my mind, from that kind of a judgment, a very small player. And the other thing you know is it cannot have lots of thorium, uranium, potassium, because it would have a significant amount of heat production, and that would change the shape of the geotherms that are preserved in the fossil geotherms that are preserved in the PT array of mantle xenoliths. Okay? So the PT array of mantle xenoliths tell us that there is heat production in the lithospheric mantle, but limited, very limited. Rick is ready to...
Yeah, the shorter answer to that is if you do it on the basis of a major element like aluminum, which is an incompatible major element, it turns out that the continental lithospheric mantle can supply all the aluminum that's in the present continental crust. If you do it on the basis of an element like barium, which is a highly incompatible trace element, the continents have something like 40-50% of Earth's barium. So the answer that you get to is the continental lithosphere could balance the continental crust and major elements, but not even come close in terms of these highly incompatible elements. So there has to be some other mechanism to transfer these highly incompatible elements to the crust. That mechanism most likely is fluid transfer in an island arc, in my opinion. I'll cover a lot of this tomorrow.
So the heat engine, the Earth is a heat engine. What do you say to somebody like me that thinks Earth's tectonics is driven by the sinking of the plates in subduction zones, that the heat being generated by the Earth is completely unimportant in driving the convection of the planet?
You should deliver the...
Somebody else wants to ask. Well, in fact, in an internally heated planet, the top boundary layer is the coldest part of the system, and that's the one that goes unstable. So the more internal heating you have, the more the sinking of the upper boundary layer is important. So when you say slabs are important, it's because this cooling is the dominant mechanism which is cooling down, and it can balance indeed, or more than balance the amount of heat that's generated internally. So in terms of tectonics, I think you have to compare the internal heating with respect to heating from below, say from the core. And the more internal heating you have, the more important is the cold upper boundary layer going unstable. So, does that answer your question?
No. And I thought it was so much better than whatever I would have generated.
So this is a seismologist speaking. In tomographic models, we have subduction zones, but we also have low-velocity zones. In particular, we have these very large provinces at the base of the mantle and other features correlated with them that are low velocities. And a slab model does not account for these structures. You can't produce them from a slab model. So there's something else going on inside the mantle than just slabs. Well, no, we don't know. I mean, the ones at the base of the mantle are probably both composition and thermal anomalies. They can't be purely thermal, is the answer. We don't know. Well, no, it could be caused by heating from below. Yes.
By core.
Yeah, by core cooling. Yeah.
Which isn't radioactive.
No, it isn't. I mean, we don't know what proportion, of course, but the point is, it's not just subduction zones.
I'll take speaker's privilege to actually push back on Barbara's answer. Basically, you can show a velocity contrast. You can't say it didn't form from recycling. You said that the structure cannot be related to subduction zone.
You're saying those could be compositional.
Well, I agree with Barbara. They cannot be solely thermal. They have definite attributes to them, particularly the sharpness of the boundary, the contrast and velocity response, that far more consistent with chemistry than thermal conditions. So I think that's an important attribute. The origin of those, be they recycled slabs that have recycled 2 billion or more years ago, or, say, injections from the core with excess iron contents, or any number of other creative ideas that have been put forth, I still don't see can be constrained in any way, shape, or form right now. They can be described seismologically. And, in fact, I've gone on to suggest that they actually have an abundance of uranium and thorium in them that could be imaged, but I still don't know how they got there.
So, actually, I had a kind of very general questions. I mean, when we talk about the heat budget, we have talked about crust and mantle composition. Of course, we know from the crust that most of the radiogenic heat is especially located in the continents, that is small portions. So actually my question was maybe in the same direction. So how we can exclude it in the mantle, especially close to the core mantle boundary, happens the same, so that we have let's say especially the radiogenic heat is accumulated in some regions while in others they are primitive. So, and how these maybe geodynamical models, they've been run, I think, and if this is geodynamically feasible, but I don't know who.
My response is going to be really heavily modified by my history in the business. I had sort of stated much earlier that I grew up academically grew up in the 80s, where I saw both my geochemical and geophysical colleagues arguing, and I mean really vigorously arguing. I know where this is from, and I know the mantle is layered. And they were just blowing smoke. I know I'm being recorded. No. No. Dan McKenzie is alive and living. But, you know, he wasn't unique. Our community used to speak exceptionally dogmatically. And in particular, a significant number of geochemists used to say the mantle is layered and it's at X depth we go into this mantle. Geochemists have exceptionally limited, and by that I really mean approaching zero resolving power for the depth at which their signal comes. It's intuition that drives me to say that the source region for Hawaii comes from the deep mantle, and the source region for mid-ocean ridge comes from the shallow mantle. It's ridiculous. I even know of a geophysicist who's going to be here this week who said that the signal seen at mid-ocean ridges comes from 400 kilometers depth. I have to, be very drunk to think that thought. But I think it's a very important conclusion to reach. Ask yourself what piece of information in an analysis of a sample informs a geochemist where that comes from. Nothing. You were going to say something, Chip.
Yeah. Hard to follow. Just referring back to your last slide and the pie chart that you showed, which you made the case that this is a guide to the possible flavors in the ice cream shop, but not necessarily any definitive answer. And we really have, really three choices of the most primitive material to select from, which you've shown here. I thought you were going to tell us or make the case that it was enstatite chondrites when you talked about the pie chart, but you didn't. And so I'm wondering if you might just, for the benefit of for all of us, speculate perhaps on why you think the Earth doesn't match any of the possible flavors of ice cream, or any combination of them.
So if I would go out of my way, I stopped my talk because I realized I spent a little too much time on some slides and didn't get to others, but I used to strongly, Marc Javois, hats off to him. In the 90s, he said, well, even before the 90s, he said, the oxygen isotopic composition of enstatite chondrite is a perfect, and he's right, match for the oxygen isotopic composition of the Earth. So you go get an enstatite chondrite, it's oxygen in the Earth's oxygen, same thing. So, in fact, from when he first started making this point till a few years ago, I thought that's exceptionally overdriving the system. That is, I'm not compelled because oxygen is a highly fractionated element, isotope system. If you look at the sun, it doesn't look anything like that. They just recently got that data. However, when you started seeing everybody's favorite isotope, titanium isotopes, but in fact I also say nickel, molybdenum, chromium, and neodymium, there are overlaps. There's not perfect matches. But I won't go into it. There's another diagram from the Paul Warren EPSL paper, and I'm compelled. You just basically have to say, first off, here's the things what you have to say. Chondrites do not all share the same isotopic composition of titanium. Why not? They should. What does it mean? What is it telling us? Marc Javois made an early observation. I think it was not based on that great of an idea, just forcing the oxygen, but as a consequence of our ability to now measure a lot of isotopic measurements, there's a lot of matches. If you look at the magnesium-silica ratio, the entire lower mantle is olivine-free almost, if you make an enstatite chondrite model. And so I actually think it's at odds with the mineral physics data and the seismology. So if, in fact, you look at the you are only a co-author, but if you look at the Marc Javois paper that came out in 2010 talking about an enstatite chondrite model, he modified his model so that there's some amount of silicon in the core and you may have a variation on that theme. So there are problems here. There are interesting, pay attention to it, observations here. I don't think this shared origin is likely. The core composition, neither Mark nor I nor others want to put that in the core. Okay? So the chondritic model, has it lost meaning? Has to be asked. And if anything, I'm going to say Javois model needs to be modified. I don't know what the Earth composition is. I am clearly going to state openly here. I get very uncomfortable about these collisional erosion scenarios that lose some amount of uranium, thorium from the other refractory elements to space. But the Javois model of exactly enstatite chondrite, no. But I will continue to maintain my long-standing view, which is chondrites are a guide. And now I've elevated the family enstatite chondrite to being an important guide, but not a requirement. Does that answer that question?
Sure.
Sure.
Any more questions? No?
I will finish by saying there are a few other slides that you'll be able to access that will provide some additional insights. And that will be on the web. I'll leave those slides in.